All right. Welcome and thank you everyone for joining our Working Towards a Zero Waste World virtual workshop. This event is co-hosted by Boston University's Institute for Global Sustainability, BU's Energy and Sustainable Technologies Lab, and the College of Engineering at Boston University. Today's topic is on reducing greenhouse gases through carbon conversion. My name is Sean Lubner, and I'm an assistant professor at Boston University in the Department of Mechanical Engineering and the Division of Materials Science and Engineering. And I'm also a core faculty member of the Institute for Global Sustainability. Today's workshop features 3 speakers. We have Dr. Hanna Bruunig, staff scientist and a deputy lead of the Sustainable Energy and Environmental Sciences Systems Department at Lawrence Berkeley National Lab, and co-director of the Hydrogen Materials Advanced Research Consortium at the Department of Energy. We have Dr. Marta Hatzel, associate professor in mechanical engineering and chemical and biomolecular engineering at Georgia Institute of Technology, and Dr. Feng Jiao, professor in energy, environmental, and chemical engineering at Washington University at St. Louis. Each speaker will give a 20-minute presentation, and after the 3 talks, we will have ample time for Q&A and an open panel discussion with all speakers. To ask questions, please use the Q&A button at any point, and we'll get to as many of your questions as we can. Another quick note, the recording for today's webinar will be available on IGS's website and emailed to everyone who has registered. Before getting started, I would also like to welcome my co-host, Professor Emily Ryan, from BU's Department of Mechanical Engineering and Division of Material Science and Engineering. And now, on to our first talk, given by Dr. Hanna Bruunig. So Dr. Bruunig is co-director of the Department of Energy HIMARC Consortium on hydrogen storage materials and head of the systems analysis team for the DOE California Hydrogen Hub ARCS. Her research group focuses on process design, modeling, and systems analysis of low technology readiness level energy systems, including hydrogen, energy storage, and negative emission technologies. She earned her BS from Cornell University and her master's and PhD from UC Berkeley, all in civil and environmental engineering. Thank you, Dr. Bruunig.
Hi, thank you, Sean. Good morning, everyone. It's really great to be here. I'm very excited to share some research today coming from my group. This is work that was really led by Dr. Fabian Rosner, who is a postdoc at Berkeley Lab, is now faculty at University of California, Los Angeles, as well as experimentalists Dr. Michael Tucker and Dr. Bok-Sun Hu, who are experts in developing solid oxide cells and conversion of CO2. So I'm really happy that you focused on this talk because I think there's a lot of really interesting questions we have about what do we do with the CO2? Do we store it? Do we convert it to products? And at what timescales? So I'll be talking about a techno-economic analysis of electrochemical refineries using solid oxide cells for oxidative coupling of methane. And there's a lot in there, so I'm going to kind of break down each of these points. But the big picture is that we are going to be reducing our petroleum product production. And that is a very linear, historically, extraction process where petroleum products are turned into things we use in our economy, such as plastics and all kinds of devices. And there's emissions that come from those conversions, as well as the use itself and the end of life. And then there's another approach that we're looking at where we could take sustainable sources of carbon, whether that's biomethane, carbon directly from the atmosphere, or some other form, and upgrade it into the products that we use today so that the products are providing the same service, ideally the same functionality of what we use today, drop-in solution, as you could say, but we're using options like renewable energy to drive those conversions. And that's the electrochemical part of this. So instead of thermochemical, we're talking about electrochemical. Now, that's easier said than done because we've thought about this for a very long time, how you can take electricity and do these services, but we're just now starting to see massive advancements in the architectures of systems and refineries around those systems that convert CO2 or methane to products that we care about, like ethylene. Now, I talk about ethylene today because it's really one of the world's most important chemicals. We use it in all kinds of reactions. We use it to make everything from plastics, as I mentioned, to detergents, pesticides, rubbers, and demand is only growing for this. And there's a serious concern that as petrochemicals are reducing, the cost is going to be changing for these products, and that would trickle down into the consumer. And we really don't want to increase the price of these critical products. We want to be identifying renewable ways of manufacturing them. And so there's a real opportunity here to focus on ethylene as an opportunity also for carbon capture and sequestration, which is another clear goal of this. Not only do we want to decarbonize industry, but we would love to actually sequester and store for very long times the carbon that we work so hard to capture, whether that's from the gases coming from a biorefinery or directly from the air through direct air capture. And plastics are an amazing way to do that and have a negative plastic product. Now let's see if it's going to advance. The method that I'm going to be talking about today is new and can leverage electricity that could be generated renewably, whether that's from hydropower, wind, solar, nuclear, things that are very low carbon in that sense, and directly convert something to the products we care about. Now, we talk about C1 carbon, but we really need to upgrade that carbon to be able to create the products we care so much about. Now, the topic I'm going to be talking about today is an oxidative coupling of biomethane. There are reactors that can do that in fixed bed, but we're really interested in converting that concept into more electrochemical systems that can leverage renewable energy and be coupled sufficiently, whether that's with a metal architecture or something that is more resilient and durable and can fit in with the way that renewables might be operating. What's also really interesting about this OCM reaction is that you need an oxidant, right? But instead of just air or oxygen, you could actually be using other forms to oxidize your methane. So instead, or your CO2. And that could be steam with hydrogen cogeneration, or that could be using CO2, or it could be using the oxygen. And so we really explore these oxidants in a really interesting approach in our techno-economic analysis to understand pros and cons of it and the operation dynamics of the system. Now, what I'm showing here is that historically we understand the system is promising, but it produces a lot of byproducts. And the more byproducts, the more complexity you have in your byproducts, the harder it is to separate. And boy, are separations costly. That's a whole nother area of research that's very exciting to see be emerging as well, is the reduction of the intensity of materials and energy for separations. But that aside, this is a serious challenge for OCM that continues to be explored, is how do we selectively produce as few byproducts as possible, maximizing the one we want, like ethylene or ethane, and looking also at key driving factors of cost, which we understand, and that is single pass conversion, so the efficiency of converting your original product to the products you want in the one pass versus multiple recycling and flow-throughs, and over potentials. So the amount that you need to drive the system to get the reactions that you want, and over potentials are basically one-in-one with wasted energy. So there are very high over potentials, and these are things that we are aware of. But for the first time in this project, we were really putting targeted numbers on what the improvements need to be. So when we talk about the potential of electrochemical systems, that's not good enough. We actually need to say, to not increase the cost of products, what is the current thermochemical petroleum-based system doing, and where do we need to get to with property targets of our electrochemical systems to be able to slam dunk this and say that we really can achieve cost parity or even lower cost in products. So that's what I'll be walking you through a bit today. So, as I mentioned, we have to understand what the current system does. And this is the ethane steam cracker that you see today. There's a couple refineries producing this at the couple million tons level in the US and abroad. And this is a steam cracker approach you see that takes the incoming ethene and converts it to ethylene with some byproducts that are either being used in energy or being sent out for either waste or for resale. Um, so there's a very high temperature that's required here. And there's also an opportunity here because there's a lot of similarities with the process that would be needed for OCM. So we can take this design and we can convert it basically to a refinery that's electrochemical refinery. Now, I just want to draw your attention to this very large product separation system. It is an extreme challenge in the industry. And I've heard time and time again people say, well, the oil and gas industry has been around for so long. They've done everything they can to become as material and energy efficiency as efficient as possible. But there's always opportunities for improving these systems as we develop new designs for thermal, for heat integration and elsewise. And so even this system, there are opportunities for improvement that can happen in the meantime while we're transitioning to this electrochemical approach. Now, switching gears to the OCM system, you also see that that product separation system is very large. You have your ethylene production OCM box here, and you have heat recuperation. So what we do is we actually take some of the byproducts from that OCM system and use it to generate energy. There's also a CO2 that has to be removed before the cryogenic cooling, and that is an interesting opportunity too, because we can actually convert that to methane potentially and reduce our original source of a consumption of primary product, which is methane in this case, or potentially biomethane in this case. And so this is the first time where we really were looking at what do facilities look like? What is the labor? What is the land footprint? What are the safety regulations? What are opportunities for improving the overall cycle and energy efficiency? And so it was really fun to be working with the team where we're designing the system and seeing what it looks like into the future. So what's the results? How did it do in comparison? So if you look at this figure, the zero is actually the thermochemical process. So everything is in comparison to that thermochemical process. And you see a few things. In blue is that upfront capital cost. And you see that, of course, that OCM island, which wasn't there, is going to be a new cost. But there's also additional costs associated with gas processing and compression, as well as refrigeration cycles that come from the new system. So we have about 100% increase in CapEx. Now, how did the operation expenses do? So that's your energy, your fuel consumption and things. Well, having the ethane as a primary product into your thermochemical facility is more costly than using than using methane, but that doesn't outweigh the overall cost of electricity in terms of our consumption of renewable energy and the prices that we were looking at. So we have this OCM island that's adding cost. That's going to be the solid oxide cell, power electronics, and those are all going to be affected by your selection of your current, your overpotential. And then you have the gas processing, which really looks at a low conversion, which leads to this high recirculation rate and ultimately high gas flows, which is going to increase the size of your system. Your feedstock, as I mentioned, has small savings compared to the electricity prices, and that's because of your high overpotentials needed for this system as it is operating today. So breaking that down more into costs, the blue again is your CapEx, the green is your operating, and the yellow are kind of like your overhead costs and things. So that could be labor, taxes, etc. So the state-of-the-art ethane steam cracker. Remember, we didn't have the data for the thermochemical plant. We had to approximate what that factory looked like. And we were able to then benchmark the prices that we got for ethylene with those factories with a very good margin of error. So that was really reassuring to see how we did compared to the factories today. So we really view even that state-of-the-art ethene-based system as a great contribution to the field for people to use for benchmarking. But look at how we did with the electrochemical facility. Clearly we have some work to do, but at least we can start to understand how we're doing, where we're going, where we might need either to advance the technology or where we might need temporary subsidies to help lower the cost of that upfront capital. And so there's opportunities for improving. So these two systems are compared at a plant scale of 400 tons per year. And we see that it's more expensive and has higher operating costs. The OCM island, again, gas processing, these things are all showing again as major cost drivers. But then you look at the breakdown and you start to see, okay, what is contributing to that overall capital and what would be the biggest, area for optimization? Now, I want to point your attention to this SOC unit. So, research being done to lower the capital cost of that system may actually not have the biggest effect on your overall performance. So you can work as hard as you want to lower that capital cost, but remember, it's only this much contribution to your overall system. So it's really something to keep in mind that yes, it is lowering costs, but maybe there's other things like this electricity consumption that's going to lead to improved reduction overall. So I'll get into that because it's really, really interesting. We think about these cell operating parameters, and the cost of ethylene is highly dependent on overpotentials and single pass conversions. Now, if you look at this graph, this kind of shows a constant voltage varying this current density doesn't really do that much to lowering your overall cost of ethylene. Now, that was super interesting because there's lots of studies banging it out about the importance of current density. Well, we found that it's not actually the biggest contribution to CapEx, the capital cost. And so over potentials, this is where we really see an opportunity. You look at that, you hold constant current density, and you're driving down your voltage, and now you're starting to see a huge benefit because it's reducing your electricity consumption, your power electronics, and also your cooling needs. Then the single pass conversion efficiency, which is also very, very important for that cost. And we see we're actually excitingly starting to get in the range of current sales prices in the last 10 years or so of ethylene. So this is really exciting to see the opportunity. So that's a high cost reduction due to downsizing product separation, which is so, so costly, and lowering electricity demand. So again, really, if you look at the capex of that cell itself, yes, it's important to lower the cost of it, but overall, it's not doing as much as lowering your consumption of electricity. And then there's something I didn't show a graph for, but this co-production of hydrogen is really, really interesting because you can actually sell that product and you can do shared capital expenses. And so that's shown here on this graph. So the technology target that we have is going to be influenced by what is our oxidant. Are we using steam with hydrogen co-production, where we actually, here is the sale of hydrogen. Hydrogen's very exciting these days. We have a lot of attention on it. Or are we just producing ethylene and really eating that cost and not having a really clear byproduct where we're selling that? And so there might be opportunities for maximizing byproduct sales, but here we conservatively assume ethylene is the primary product. And so again, going back to my point that it's really important to have targets for things being done in the lab. And here we're putting out some suggested ranges where today we're looking at operating voltages, single pass yields, Faraday efficiency, CO2 side reactions, and hydrogen co-production. And we really need to get it way further to be competitive with the petrochemical system. Whether that's a fair target for a sustainable, clean economy is up to, our politicians and you, but this is the way we work and this is the world we live in. And you know what? Engineers work really well when we are given constraints. And this is the kind of challenge that we can still handle, although it does delay that timeline for when we can effectively have cost parity with petrochemical based pathways for the products we have in the economy today. So yes, we can do it today with the technologies that are in the lab and on the shelf and being piloted. But to have cost parity, we have a marching timeline of progress that still needs to be made. So just briefly in wrapping up my section, I'll just note that there is great work being done at the bench by Dr. Hu and Dr. Tucker on OCM research. This is looking at the temperatures that need to be achieved, as well as the structure, the architecture, switching to more durable systems like metal-based structures, and looking overall at some of the performance today. that is going forward from the guidance we gave in our TEA, or techno-economic analysis. So, for example, OCM could be complemented with proton conducting cells for ethane dehydrogenation. This could reduce product recirculation, separation costs, focusing on certain products. And then the metal-supported cells, as I mentioned, can offer system-level integration advantages, including being able to handle different fluctuations in temperature, as well as system design flexibility, especially for these bifunctional cells. And there's been some great success in moving this towards commercialization, working towards these over potential that we targeted, as well as improved conversion. And with that, I'd really like to thank you for your attention, and I'm looking forward to the discussion later. Thank you.
Great. Thank you so much, Dr. Bunig, for that really important perspective. And so as a reminder to everyone who's listening, we will have all questions responded to collectively at the end, but you can submit a question at any point during the talks using the Q&A button at the bottom. So our next speaker will be Dr. Marta Hatzel. And so she is an associate professor of mechanical engineering and chemical and biomolecular engineering at Georgia Institute of Technology. Hatzel's research group focuses on exploring how to electrify catalytic and separation-based processes to enable sustainable industrial systems. Her group works on materials, characterization, and system analyses for electrolysis, fuel cells, desalination, and solar energy conversion processes. Among many awards, Dr. Hatzel has received the Moore Inventor Fellowship, O&R Young Investigator Award, Sloan Foundation Fellowship in Chemistry, and the NSF Early Career Award. Dr. Hatzel currently serves as a senior editor of the ACS Energy Letters Journal, and we are now happy to have her speak with us.
Okay, thank you for that introduction. I'm happy to be here today to present on some work that my research group has done at Georgia Tech on bipolar membrane electrolysis for combined carbon capture and conversion. I definitely want to highlight first and foremost the graduate students and postdocs that conducted this research, and they had a nice press release. And so here they are: Dr. Sung, who's a postdoc, Carlos Fernandez, Dr. Fernandez now, who is a postdoc at Stanford, and Poe Huang, who is a PhD student at Georgia Tech. And so I guess all of us here are interested in this idea of CO2 and the role it's going to play in the environment, and the role humans can play with it, both in a positive and negative way. And right now there's a growing interest in hopefully reducing our carbon footprint by increasing energy efficiency of most of our technologies and moving away from fossil fuels. But there is some thoughts that we also may need to develop technologies like carbon capture to start to remove carbon dioxide directly from the atmosphere, or carbon capture directly from flue gas that exits power plants or industrial sites. And so what you do with that carbon dioxide that you capture is still definitely a question that needs to be answered. And so, yeah, generally here, everyone's quite aware of this, the rising CO2 in the atmosphere. And as we know, what goes up must come down. And so there's been a lot of researchers starting to look at what are our goals for decarbonization globally. And there are a lot of things that we can do in terms of engineering with respect to our decarbonizing our electricity and heating, decarbonizing our industrial sector, our transportation sector, our building sector, and then other sectors as well. And what my research group at Georgia Tech looks at is specifically on the role that low carbon fuels are going to be playing for industry, aviation, transportation, the power sectors. As you can see here, there's the gigatons of CO2 on your y-axis, and then the projected years. And then these blocks up here kind of detail some of the benchmarks that researchers have put forward as key milestones to meet these net zero emissions. And these blocks highlighted in yellow really are reliant on widespread electrification, and then also the use of low carbon or no carbon based fuels. And so What we believe is that electrification may enable low carbon fuel production via these electrolysis-based technologies. And you heard about in your first talk, one electrolysis-based technology based off of solid oxide-based systems. And then I think our next speaker will also be talking about these electrolysis-based systems, but I just want to highlight electrolysis and electrification and the production of low carbon fuels and chemicals are going to be very important to meet these net zero goals. So when looking at electrolyzers from a bench scale or experimental systems perspective, you have to often think about the catalysts that go into those electrolyzers, the reactors, and then also the process integration. And so my group at Georgia Tech really has spent the last decade looking at designing these catalysts and understanding how to design active, selective, and stable catalysts. Obviously, active catalysts and stable catalysts really go into your economics, as does selectivity, but selectivity is really geared towards decreasing your need for downstream separations, which, as the previous speaker mentioned, can be quite energy consuming. And so we've done quite a lot in this catalyst development space, but then we always like to take that catalyst development and start to move it into reactors that look something like this. When you move from just looking at the catalyst performance, you're really just looking at the reaction. But then when you start to put these catalysts in electrochemical systems, you're really starting to look at how reaction and transport play a role together, and you're getting really a cell performance. And so this is the process that we use to examine the effectiveness of these technologies. But more recently, with the help of collaborators, we've also been starting to look at how you can take the performance that comes out of a bench scale system and use it to inform process engineering models to understand complete system bottlenecks and how you can integrate renewable energy effectively into these systems. And so I just wanted to emphasize that there's quite a lot of work that needs to be done at that science and that atomic level. And then it needs to move up into the bench scale level. And then ultimately, these process models are very critical in understanding the true bottlenecks of these systems. So electrolyzers, if you're not familiar with them, are widely used today for the chlor-alkali industry, and then also more recently for hydrogen production. And it's a very simple architecture where you have an anode, a cathode, some sort of electrolyte. And historically, the hydrogen PEM water electrolyzers have really focused on differentiating these reactors based off of the membrane that is used to separate the anode and cathode, and by the anion or cation that crosses to maintain electroneutrality in your electrochemical system. And there's many benefits and positives of each approach. Alkaline typically tends to be cheaper. PEM tends to have higher performance. But this has largely been the baseline for our work in CO2 electrolysis. And that begs the question, are water electrolyzer reactors architectures optimal for CO2 electrolyzers? And we at Georgia Tech have been working in this for the last couple of years and realized that there's quite a significant difference when looking at the electrolytes, the reactants, the products, the catalysts, and then when looking at what a chemical fuel or a chemical fuel process looks like. It's very different when looking at carbon dioxide than looking at chlor-alkali or looking at water electrolysis. And so to drill down on some of these differences, if we use an anion exchange electrolyzer, which is typically used for water electrolysis, and try to just substitute water with CO2, the CO2 is integrated into the cell, but because you have an alkaline electrolyte, an acid-base reaction occurs, converting CO2 to carbonate. And then CO2 is in carbonate, and because electroneutrality must be maintained in these systems, carbonate can cross over the anion exchange membrane, which because this carbonate or bicarbonate are anionic. And what you start to find is that the CO2 that you're supplying to the electrochemical cell, which you hope to react and convert to some chemical or fuel, is actually being lost across the electrochemical cell, needing for the regeneration of this catholyte. And it's been estimated that actually 50% of the energy input is of these electrochemical cells and systems actually goes to regenerating the gaseous CO2 that is lost to carbonate, and not to the transformation of CO2, which is counter to the point of your CO2 electrolyzer. Another challenge with CO2 electrolyzers, especially if we're thinking about integrating them with carbon capture from, again, direct air capture systems or from flue gas, is that you need high purity CO2. And so there's many different systems that are needed between the capture process and the electrolyzer. And so because of that, when we actually start to look at the energy demand, we start to see that the energy associated with the catalysis is actually quite low compared to the capture energy, the separations energy. So when starting to engineer these systems, it may not be adequate to just draw a control volume around our electrolyzer. And we really just need to start to look at the upstream integration steps to ultimately drive the total energy of our capture and conversion process down. And so this brought us to rethinking what electrochemical reactor architecture might be ideal for carbon capture and CO2 electrolysis. And what we were really thought that the bipolar membrane electrolysis of bicarbonate solutions or carbonate solutions had several advantages over traditional anion exchange-based CO2 cells. In a bipolar cell, you have not an anion exchange membrane or a cation exchange membrane. In a sense, you have both, but they are combined in this membrane, which is called the bipolar membrane. The charge difference between the membranes allows for water to diffuse rather than an anion or cation, and then electroneutrality is maintained through the dissociation of that water and the production of protons and hydroxide at the membrane interface. This production of acid is important because we can take the bicarbonate solutions from that carbon capture solution and we can convert to CO2 within the electrolyzer architecture, and then can catalyze the CO2 to a chemical or fuel. Here, I'm demonstrating the conversion of CO2 to carbon monoxide. Again, you can have an alkaline anode, so you can use a cheap material at your anode, such as a nickel-based material. Another benefit of this cell is that you have zero carbon dioxide crossover because of the anion and a cation exchange layer, not allowing for carbonate to cross over in this electrochemical cell. So this is a simplified version of what we're trying to do. Take a very complex system of capturing carbon dioxide, purifying the gases, and feeding them into an electrolyzer cell, and taking the carbon capture solution that comes from an air contactor or again, flue gas, and sending it directly into the electrolyzer. And by eliminating all of those different components, you often can drive down costs. There are significant challenges with this. One is that it's very acidic in those cells. And so you end up producing much more hydrogen over C1 or C2 products like carbon monoxide, as shown here. So you have excessive protons and you have high overpotentials associated with that thickness of that membrane. And so these are two critical things that need to be worked on. Another challenge is that because you have acidic conditions, you often can have low amount of CO2 that evolves within the cell. Again, we're feeding carbonates and bicarbonates to the cell, but we want to react CO2. And so we need to be able to shift the equilibrium to generate enough gas so we don't have mass transport limitations. This diagram kind of shows you how the Faradaic efficiency for carbon monoxide decreases as the pH changes in the cell. And so when we started to look at this from an electrolyzer point of view, we really identified two problems. We need acidic conditions to generate CO2 within the cell, but we need alkaline conditions, ideally, to catalyze the conversion of CO2 to carbon monoxide instead of hydrogen gas. And so the approach that we went about was looking at how do we use catalysts that potentially can catalyze CO2 under acidic conditions, and and how can you get high intrinsic activity to CO2 around a pH 2 instead of neutral conditions or alkaline conditions, which is traditionally used in alkaline anion exchange membrane electrolyzers. And so this is a little bit about the single atom nickel catalyst. It's not a single atom per se, but it's an atom that is within a scaffold. And it has been previously shown in gas phase systems to have a low overpotential for CO2 reduction to carbon monoxide. And so, but it had not yet been demonstrated in an alkaline bicarbonate based system. I will mention that we did this work with Professor Oon's group in KAIST University. And this kind of shows you what these single base nickel atom catalysts look like. As you can see, they have the single atoms, which are basically stabilized by these nitrogen compounds and carbon scaffold. And so they tend to be quite stable over long periods of time. And this is just some X-ray characterization, which demonstrates that you have, with a single nickel catalyst, the same nickel bonding that you can see with the nickel. This blue line is the precursor material that's used to generate the catalyst. So this is exactly what the reactor architecture looks like at the macro scale. You dissociate water, you have this acid-base reaction with bicarbonate, generating CO2. CO2 then can interact with an electron to generate carbon monoxide. Here's some performance data to show you what this looks like. You have higher current densities. We start to see a decline in our selectivity towards carbon monoxide. The orange shows you the carbon monoxide. The green shows you hydrogen. But at moderate current densities of 100 milliamp hours per centimeters squared, you can see generally very high selectivity toward carbon monoxide, which was a substantial advancement at this time. This is to show you the CO Faraday efficiency over time. You can see that the carbon dioxide electrolysis declines with time because of accumulation or loss of carbonate-based CO2 to carbonate. The bicarbonate electrolysis also declined with time, but this was because it was not at a steady state. We were generating too much alkalinity during the reaction. So if we continually sparge with CO2, therefore maintaining the pH and the ideal pH, we can get quite a stable operation at near 100% Faraday efficiency of carbon monoxide in these systems. Here's a little bit of a spider chart to show the performance differences. The key to note is that with these bicarbonate solutions, we can get high carbon dioxide utilization, which was our goal. But the cell voltages tend to increase because the bipolar membranes are a little bit more resistive. Where are we going next? So we're interested in carbon monoxide because it can be fed to a Fischer-Tropsch process, and a Fischer-Tropsch can give us these liquid carbon fuels. And so we now have kind of been optimizing this electrolyzer, but we want to now start to integrate this to our Greenwells program with a renewable energy, which is going to create a variable profile, variable overpotential, and then feed it to Fischer-Tropsch process to make liquids, higher carbon-based liquid fuels and chemicals. And without that, this is my summary. Bipolar membrane electrolysis could be useful for carbon capture and conversion. We noted that you need to have acid stable and selective catalysts to get products like carbon monoxide. We've been able to demonstrate that. And this is a little rendering of what, the future of chemical manufacturing might look like. Hopefully it has a low footprint. Hopefully it's run by renewable energy. And hopefully it uses waste-based feedstocks like carbon dioxide instead of fossil fuel-based feedstocks. And with that, I want to acknowledge my students, and I'm happy to answer questions during the final portion of today's webinar.
Great. Thank you, Dr. Hatzel, for this really good overview going truly from atoms all the way up to full system scale. So our third and final panelist speaker will be Dr. Feng Jiao. And just as a reminder again to the audience, we're already seeing questions coming in, but you can ask questions at any point during the presentations using the Q&A button down on your Zoom screen, and then we will respond to all the questions collectively at the end of all the talks. So Dr. Feng Jiao is the Elvera and William R. Stuckenberg Professor in Energy, Environmental, and Chemical Engineering at Washington University in St. Louis, and he also serves as the director of the Center for Carbon Management. His research group is developing innovative electrochemical devices to address critical energy and sustainability challenges. Dr. Jiao's contributions have been recognized in many ways, including his election as a Fellow of the Royal Society of Chemistry, an NSF Career Award, and recognition as a 2020 Emerging Investigator by the Journal of Materials Chemistry A, and a 2020 Scialog Fellow for the Negative Emissions Sciences Initiative. Thank you, Dr. Jiao.
Thank you, Sean, for the introduction. Let me start sharing my slides. Just a second. Does that look good? Okay, so thank you for the opportunity for me to share our research on CO2 electrolysis systems for chemical and food production. So today I'm going to mostly focus on the electrolysis part. So the previous speakers talk about the tech economics, talking about the integration of carbon capture with the conversion. Very nice layout of the foundation. So because it's already mentioned, the CO2 electrolysis is one of the technology we could considering to convert the carbon dioxide into useful chemicals. So today I'm going to briefly go over the technology itself and tell you a little bit about our thoughts on how we can go from lab scale all the way to commercialization. What's the key challenges we need to address? So just to remind you, this device we are talking about today now is polymer membrane-based systems. Of course, previous talks also mentioned solid oxide systems. They are operate at different temperatures. So for us, we mostly focus on the room temperature or near ambient temperature systems. The polymer membrane plus two cathode electrode and anode electrode, that actually is a very important research areas we are actually actively involved. So this is one of the issues the previous actual speakers also mentioned is the carbonate formation. If you conduct CO2 electrochemical reduction in aqueous electrolyte, you cannot avoid the formation of carbonate. And the carbonate will form on the cathode and also cross over to the anode side. And you are going to run into a situation is you're going to lose a significant amount of the CO2 feedstock, but at the same time, the carbonate also will destroy the gas diffusion electrode and hurt the stability of the system. This is a well-known phenomenon starting about 5 years ago. People starting to pay attention to this phenomenon. And there are a lot of interesting research has been done to try to address this carbonate formation. So one of the approach is to separate carbon dioxide to carbon monoxide and carbon monoxide to multi-carbon product kind of conversion. So this is we call the tandem process. So why the tandem process can be better than the direct CO2 electrolysis? So solid oxide systems mentioned, I just briefly mentioned, is the fantastic technology. Actually now being commercialized by Topsoe, a company based in Denmark. On the top right, you will see is this chart, the performance chart published by in Science a few years ago. And you can see compared to low temperature membrane-based electrolysis technology, solid oxide electrolysis actually can achieve pretty decent current density over 1.5 amp per square centimeter at very low voltage. So this actually makes it highly energy efficient systems. However, solid oxide system can only convert CO2 to carbon monoxide because the thermodynamics, it cannot form multi-carbon bond in the system and form more interesting chemicals. We are very interested as a society. For example, ethylene, talk a lot in the previous two talks. and acetate. This is one of the substances we are particularly interested. There are bicarbonate mediated electrolysis process also being developed, and bipolar membranes as being discussed by Marta. These are the new areas could potentially address these carbonate formation issues. In my research group, we mostly focus on taking the carbon monoxide can be produced out of CO2 and further upgraded to more valuable compounds like acetate or ethylene. So I will start with my presentation on the discovery of acetate formation. This is a very unique phenomenon only occur in CO reduction. So at the beginning of our research back to about 10 years ago, we looked into the flow cell systems. In the flow cell system, our original motivation is trying to enhance the reaction rate because we know carbon monoxide, carbon dioxide, they have very low solubility, but rely on a gas diffusion layer, you can enhance the mass transport, and therefore you can achieve very high current density. This is the original motivation, but we accidentally discovered very interesting phenomenon. This is shown on this slide. So we study two different copper catalysts, and in using the flow cell, we can quickly switch the feedstock gas. So for example, we can feed carbon monoxide in the beginning to the reactor, then quickly switch to carbon dioxide. Then after a period of time, we can switch back to carbon monoxide and repeat again. So by doing so, we can investigate the catalyst performance at different gas feedstock. So what we found is acetate become a significant product when we feed carbon monoxide to the copper-based catalyst system. And this kind of phenomenon can be reproduced by using different copper-based catalysts. On the left is we call the OD copper. It's also referring to the oxide-derived copper is a high surface area copper catalyst. On the right is the micron-sized copper. So very interestingly, we found is acetate can be formed at up to almost 20% efficiency selectivity under CO. So we actually go one step further to design a scalable CO electrolyzer systems using a polymer membrane, which is anion exchange membrane in this particular case. So how we configure the cell design we used here is we call the zero gap design. Basically, we put the cathode and anode right next to the membrane material. And on the cathode chamber, we only feed the gas, okay? So basically we feed the carbon monoxide gas into the cathode, and we collect any gas product from the cathode side. And on the anode side, what we feed is alkaline supporting electrolyte. Basically is a potassium hydroxide. Then it flows through the anode chamber, and we will collect the liquid product. So any liquid product produced on the cathode side, based on this cell configuration, actually cross over to the anode side. Interesting, we found is by choosing a suitable catalyst for the anode, we actually can promote the selectivity towards acetate. This is something I'm going to show you in the next slide. So when we're choosing a nickel iron oxide to be the anode catalyst, what we found is nickel iron oxide not only is a good oxygen evolution catalyst, which is commonly conducted in CO2 or CO electrolysis system, but also the nickel iron oxide is a good catalyst for partial oxidation of ethanol into acetate. So basically, by using this catalyst, we actually purify the product stream, the liquid product stream, to be a highly pure for acetate. So, with the further engineering of the system, what we found is we can get up to almost 95% of purity of acetate at the anode side. So this is the data. We continue to operate the system. It's a 5 square centimeter electrode size for over 120 hours at 300 milliamp per square centimeter. We replace the electrolyte, supporting electrolyte every 24 hours. The system is very stable, and we can achieve almost 50% of acetate even after 120 hours continuous operation. Also, we actually pay attention to the product concentration, because if you produce a liquid product at very diluted concentration, this is not going to helpful for commercialization, because the separation cost will be dominant the overall cost of your product. This is something also mentioned in the first talk, is when you engineering the whole system, you really need to pay attention to all the components going to involve and contribute heavily to the overall cost of your product. So for acetate, what we found is we really need drive the concentration as high as possible, which in turn will reduce the separation cost. So in this chart, what we found is it's feasible to drive the product concentration almost up to 7 mol, while at the same time, you can see on the right, the separation cost will actually drop significantly compared to the electricity you need to pay for the electrolysis part. So we take one step further. So previously, I show you is about a 5 square centimeter electrolyzer. In the past 2 years, we actually focus on how we can scaling up the system to a kilowatt unit. And this will go beyond single cell. Basically, we are working on 2 stacks. Each stack have 500 square centimeter total electrode area. The first stack is doing CO2 to CO conversion. The second stack is to do CO to acetate conversion. And by coupling these two together, what we achieve is a kilowatt scale demonstration of this tandem CO2 electrolysis system for acetate production. So, of course, this is not easy. There's a lot of challenges we are facing for today. Because limited of time, I just briefly share a little bit thoughts we experienced, some of the challenges we are in the past 2 years in the scaling up effort. So for larger systems, sealing of the reactor actually has become critical. For small reactors, when you compress it, usually you can get a pretty good seal and there's no leak. But for larger cell, you cannot over compress it, okay? You need to compress it enough, but not over compress it. Because when you over compress it, depends on the gasket material and the electrode, you may damage the components. So this is a lot of engineering work. We have to figure out how to compress the stack properly and maintain the function and also prevent any leakage. The other one we found is the mass transport. So the mass transport is particularly important when you work with larger reactors. So you have to deal with the reactant delivery and also the product collection. So if the reactant cannot deliver to the active site on a larger electrode, then you will experience is some of the catalysts just driving the side reaction, okay? When they leak off, they cannot have access to the reactant. At the same time, if the product stuck in your system for long period of time, you experience is the product will diffusion crossover and got consumed by probably by anode, could be doing other side reactions in the system. The third item I want to bring up is when you're doing scaling up, we also need to pay extreme attention to the quality. So we really need is a uniform electrode, which means if you build a electrode at 100 square centimeter, I want every square centimeter on that 100 square centimeter electrode just identical. This gives us a lot of challenges in terms of how we can uniformly load the catalyst to the gas diffusion layer. How we can maintain the membrane material is mechanically and chemically stable and uniform. And there are many other challenges we are facing in terms of the quality control. So also when you're doing larger systems, because the overall CO or CO2 electrolyzer operate roughly energy efficiency of about 50%, which means the other 50% of energy will become the heat. So temperature management become very important to these larger systems. We actually spend a lot of time trying to figure out Should we do active heating or active cooling? How we integrate the cooling system or heating system in the larger stack? This is one of the major efforts we actually still keep doing it in the lab. Also, long-term stability. So glad to report, we're actually pushing this a little bit further. Previous I show you, we can do 120 hours, and I'm going to show you a little bit about our initial result for the larger systems. We can do slightly over 100 hours. Now we actually can close approaching 1,000 hours by this moment. Product separation and purification, very important for practical applications. And of course, at the end of the day, cost is the most important thing to determine whether this technology can be commercialized or not. So this is the kilowatt scale performance. It's 1,000 square centimeter. We achieve about 35% of acetate selectivity. And of course, you will see the hydrogen Fe is relatively high. So we are still working on trying to suppress the hydrogen evolution in the system and trying to further improve the acetate selectivity. But for now, it can stable for 124 hours. And on the right is the product. It's almost 100 liters, 1.5 mole of potassium acetate with more than 95% of purity. So working with the company side, we're also doing several revision of this reactor design from the kilowatt scale we just reported, and to the second generation we just completed at WashU. And now my student actually, and also the company working on the third generation, which is much larger systems. Hopefully by next year, we can further scaling up this system to 10 kilowatt unit. I will share more results in the near future. So I only have 2 minutes. I want to touch on one last point I want to emphasize is, can we go beyond just chemicals? So the problem for chemicals is it's indeed have a large market. For example, acetic acid has a $9 billion market, equivalent to 16 million tons a year. However, if you look at the CO2 emission, we're at a gigaton scale. So we're actually inspired by some of the others think about, can we go beyond chemicals? So the one of the things I'm personally very interested is, can we convert CO2 into food? These are just 2 issues, CO2 emission and food shortage security. So work together with Professor Rob Jenkinson at the UC Riverside. We actually published a paper in Nature Food 2 years ago. We actually assembled the team with electrolysis part, CO2 to acetate, then the biological part, acetate to food products. So we actually demonstrated successfully acetate can be utilized by biological cultures like yeast, mushroom, and algae. And in the future, we want to work on can we make the plants grow without photosynthesis? This is something we call food production without line. And this is the first prototype we just demonstrate as a part of the NASA Deep Space Food Challenge. It's completed in August. We demonstrate this at Ohio State. We successfully grow mushroom just out of acetate, produced out of CO2. We are very excited about this. We think electroagriculture could change the ways we do farming for a sustainable future. And the editor, Rob Service, actually write a very nice article about this kind of technology. Think about whether we really can grow crops without sunlight. So with that, I will conclude and acknowledge my team and the funding agencies and the collaborators. Thank you, and happy to answer questions at the Q&A.
Great. Thank you very much, Dr. Jiao. So I'll now invite all of our panelists to come back for open Q&A. We've got a few questions from the audience, but as a reminder again, you can use the Q&A button at the bottom of your Zoom to submit a question at any time, and Emily and I will try to make sure that those are relayed to our panelists. But maybe to kick things off, I really want to think more about this question of scale. So I'm really glad that you kind of ended on that note. And I noticed that on everyone's presentation, there's this interesting parallel of considering the really nitty gritty down to almost atomic level science, but then having to think about how that connects back up to the full system. And I think especially with carbon conversion, the scale of the problem is easy to miss because it is so large, right? We use this word gigatons of CO2, and that's almost too big to be intuitive. I think, one calibration point is it would take more energy than the entire US grid to capture the amount of CO2 we need. So this question is to all the panelists. Maybe I'll first direct it to Dr. Briunig. What sort of challenges might uniquely arise from trying to tackle problems at this scale that is, truly gigatons that one might not normally have to think about?
That's really a great question. Thank you. I think when I think about scale, I think about, are we talking about distributed or centralized systems? So the system that I showed is really a refinery. We use that word not lightly because I think people think, oh, electrons, you can just hook it up anywhere, you can do this anywhere, and that's the power of electrochemistry. Actually, in many cases, that's not going to be the case. And that could actually come down to things such as what trucks are coming by to pick up the product and deliver it. How do you even transport carbon monoxide? It's really a difficult thing to transport. It's not easy. So to say you have CO as a product is we're still dealing with supply chain issues at these scales. And so I think it's going to create a lot of questions for where do we locate this in communities? And so one thing that I've been thinking about a lot is this question of any infrastructure done at this magnitude that you just mentioned is going to have community buy-in, and it's going to be seen by the communities. So this is not something we can just hide away in the forest, right? So I think we need to be very, very strategic with partnerships early on and do a lot of education and be very transparent about what we do and don't know. So that's the things that I think about at this kind of scale of deployment.
Great. And Dr. Hatzel or Jiao, anything that you want to add to that? I think
I guess I'll just add on. I think that's exactly a point that I think that there's right now at this stage of the development of these technologies and processes and systems. The good news is I think we need research at all scales because we do need the catalysis scientists to come up with durable catalysts, but we also need people to be starting to move to the problem as Feng Xiao mentioned, the leakage and all of these issues. We can't ignore them forever, and so it's a good news. We need people at all these scales and to scale things up. But in addition to looking at scale, I think also starting to look at how you how do you run this off grid, behind the meter and things like that. Because as we mentioned, you're not going to have access to the different power generation everywhere. And so I think that's going to be an important part, is starting to look at this off grid and seeing how durable and resilient these systems operate is also important for scaling.
Yeah, I think both very important points that there is no way for any of these solutions, if they succeed at scale, to be invisible, because at the scale, it will necessarily have to be something that's fully integrated with society. And also it means that we'll have to think about how does it interact with large scale energy that might not be able to just completely dominate the grid.
Maybe I'll do a follow-up question we just got from the audience that goes nicely with what we were just talking about. The question is, what support do researchers need to begin to have early and often conversations with communities to prepare for the needed facilities, risks, et cetera? And I think this is a broader conversation we need to have as scientists, not just about this topic, but the general kind of transitions of energy. So I don't know, maybe we'll switch up and see if Feng has anything to say about how, or if, since you're working with a company, do you guys think about the communities that you'd be impacting?
Definitely. So one of the projects we are got involved with company side is trying to produce proteins as a food substance. Of course, when you're talking about the food, everyone got a concern. Oh, you are chemically synthesized and kind of food is not nature produced. So you have to sort of explain to the community what is the food you are going to produce, they present any potential hazard to them, This is public acceptance. It's very important to be part of these research efforts. Otherwise, even you can produce it, no one is going to eat it. So you kind of waste your money and efforts trying to create this kind of technology. No one going to use it. Very important point, yes.
Hannah, the skills that you look at, is this something you also think about as the community engagement?
Yeah, and in fact, I'm a co-PI of the California Direct Air Capture hub that was funded, and it's called CalDAC because it's actually called a community-driven one. And so what we're doing is we're trying to understand the key performance indicators that communities need. And so there's a teams that we've engaged in the Central Valley of California where a lot of the storage facilities for CO2 or CO2 conversion to products might happen, where we're working with people who are already on the ground working with this partners. We're not trying to cold call the community stakeholders themselves. We're working with experts who are doing that already, who know how to engage, who has the trust built up. And that's the first mistake to not make, is really like leverage all the decades of work of trust being built and listened to. And I think just quickly, one thing I'd mention that we're all learning is the pace of a community stamp of approval technology might not be at the pace that we feel at the urgency of climate change. These two things have been in conflict for many, many technologies, whether that's bioenergy, carbon capture, hydrogen. There's many reasons why we need to potentially go slower. And so this is why it's really important to create, I'd say, a pathway for how we do this right. So that question, I think, is an open question. I don't think anyone has fully understood that, but we're learning as quickly as we can. And so these kind of hubs are great. Maybe a CO2 conversion hub would be the same thing to gain that kind of experience with community input.
Yeah, so it's interesting to reflect on how you're all thinking very carefully, both about the actual science, but how that needs to fit in to the societal perspective, the scalability. And this also, in my mind, leads to a sort of theme in some of the other questions of kind of engineering versus science, which is sort of a continuous smooth spectrum. Maybe I'll first direct this to Dr. Hatzel, but question for everyone. In your view, how does this lay out between needing fundamental new scientific advances versus needing to just get enough people on board with the immense engineering challenges to implement it?
So is the question, what is the contributions that each can play, or?
So from the parts that you're familiar with, where do you see a lot of potential for, big improvements?
Okay. Yeah. So historically in the CO2 electrolysis, I think a lot of the basic science has focused on the catalyst design, and in changing it to maybe get a slight difference in selectivity. I think in the next decade, it might be moving away from selectivity and more focused on how can you use your science to make a more durable and low cost catalyst might be the focal points, or maybe should be, to mirror the commercialization needs. And so, yeah, from a science, that's my perspective on, and then also how can the science inform? We're starting to see that a lot of the selectivity is also heavily tied to transport-based questions, and while that has been heavily studied in fuel cells, it's been less examined, I would say, in the electrolyzer world. So I'd say in the basic science side, those are some emerging needs and directions. And then on the engineering, I think we are always fixed on these reactors, plate and frame reactors, and that we've used for decades. I think that there's opportunities to innovate in reactor design and space that I think we've developed many modular systems since plate and frames. And so I think that chemical engineers and mechanical engineers can play a large role in maybe innovating in that space.
Yeah, I'll quickly, maybe short follow-up question. You mentioned the degradation. I feel like that's a specifically linking property where it can be very challenging to study scientifically, but has huge impact on the potential commercial viability. Maybe after you, there's a techno-economics perspective on that, but what sort of challenges have you seen in trying to understand degradation and connect that to the technology?
So yeah, so one part of studying degradation is the environment that you're studying it within. And so if you're doing a very small scale systems that doesn't at all translate to a larger scale system, then it might be hard to study durability. Again, PhD students need to hopefully graduate in 5 years. And so having them run a cell for 20 years may not be an option. So I think that those are there are some challenges. Those are usually longer experiments and then bigger experiments, and so that's maybe where like private academic partnerships can maybe play a role, where that you can get some academic research on durability if we start to have these local test beds, and also and again, this goes to potentially, needing more funding and hubs and so forth, so that academics can engage in durability, but maybe it doesn't have to be located at their individual lab. Maybe it could be located in a centralized national lab and so forth. So academia and everyone's going to be well suited for different research, but it's a challenge in a single lab to do some of these experiments.
I wonder, Dr. Bruenig, if you can comment on sort of from the techno-economic analysis perspective, if there's a strong way for scientists to use that to motivate more engagement from industry or from larger entities to support degradation research and studies.
Yeah, it's a great point. And you kind of said that atoms to systems pipeline. One thing we haven't talked about yet is the role for machine learning and ways to speed up this kind of selecting of material properties and materials themselves without having to do the experiments at all. And so that's large computing systems and others. And that's the kind of stuff that the companies can't do themselves necessarily, but they engage with universities and national labs where we have user facilities and we have supercomputing capabilities. And so we've seen advancements on this on Catalyst side, where there are maybe 6 pathways for degradation, and they're going to happen preferentially depending on what real world conditions you have, as Dr. Hadsell noted. And so we need to really partner with those industries to say, hey, how are you operating it? What is your operation cycle? What is your bare minimum expectation for pressure and temperature and scale? And then we can take that back and like you noted, are the experiments we're doing 1x or 1000x different? And so that's the kind of data share that has been really exciting and I think really kicked off lately. And as was noted before, we need the basic fundamental advanced science moving together despite the urgency of the situation that we have.
Maybe building off of your initial question on the science versus the engineering, there's one thing that I heard, at least Dr. Zhang say, uniformity at scale, right? So we all start at very small scale, but uniformity is critical to having this performance and not having that degradation, hopefully. My question for you is going to be, what are the challenges there? Is it that, do we have the techniques to fabricate what we need with the uniformity at the scale we need, or is that part of the challenge? Not just finding the right materials, but the manufacturing and the fabrication procedures that will get us the quality that we need.
So it's so we know the technology have a different readiness levels, but so does to the manufacturing. So when the structure of the electrode become complex, control the quality become more difficult. So of course, in research labs, we don't care. We add 2, 3, 4, 5 components in it. But in real world, when trying to manufacture at a scale, these pose significant challenges for people really go to, say, square meters or even tens of square meters of electrode. Of course, this is some kind of research most of the time done by industry people rather than the academia side. So we're actually trying to look into, say, let's get it to tens of or 100 square centimeter scale, whether we foresee some of the challenges. Maybe the electrode is so complicated, it's just hard to manufacture at the scale. Can we simplify it? So this is something we're actually actively looking into. Can we maintain some of the properties without complicate the system too much?
And I'm curious, sort of in your experience so far, trying to really scale these up, it sounds from the discussion like it would be most helpful to have that be a continuous feedback loop from the start, where someone's ideally thinking about the big picture simultaneously. But very often that's not how it happens. It kind of start off with these discoveries, and you don't want to discourage them too early. In hindsight, would you say that the way that you have ended up approaching this, or the way you see other researchers approaching this, is the best balance between those two? Or would you advocate for sort of tighter integration across scales earlier on?
So for CO2 electrolysis, it's a little bit too early, probably. There are a lot of innovations, the cell configurations, everyone have their own ideas. I don't think the community settle down are, one particular one will be particularly promising for scaling up and commercialization. So for example, if you configure a reactor with bipolar membrane, it's very different from if you configure with just an exchange membrane. So I think because it's early stage of this technology, I a little bit hesitated to say, let's just work on the scaling up. So then I just pre-select one particular configuration. Everyone need to focus on that one. It may not be the best for the community to grow. That's my opinion, of course.
Actually, I'd be curious to hear the opposite end, because one of the first things I remembered hearing was the over potential is critical based on the TEA analysis, which might not always be obvious. So I wonder if there's the same outlook from Hannah.
Yeah, maybe I can comment on it. So we got this topic that I just presented funded through an internal grant, and Dr. Elber is aware of these. They're research directed internally because we can't get funding to do it. It's too high risk, too high reward kind of stuff. And that actually was the coupling of a techno-economic team with people developing the architectures. And to be perfectly honest, we spent the first 6 months just learning each other's language. Like we didn't know what we needed. We didn't know what we had or unknowns, what was important. And we had to set up the math equations to even define the system. And so that upfront work is a dance. And I agree with you in some sense that if you don't have enough experimental data, there's nothing for the TEA team to do other than create big error bars. And so there's a point where if you want a robust mathematical model, and then to start doing machine learning for selection, you do need to have developed enough experimental data to really do that. But that being said, I do think very low TRL systems, even photoelectrochemical systems that are like TRL 1, right? Maybe, maybe 0. I don't know, depending on the material. We're already doing TA for those, and they are really hard. And that's why you need a couple years just to do the TA part. So I would say it's still important because, as you noted, Dr. Ryan, we did identify things that are important. For example, having a system that can handle a very large pressure differential is actually quite important, because when you have renewable systems that are fluctuating very rapidly, you don't want this large compressor system up front. You want actually ambient systems to come into it. And that can lower costs. And you wouldn't know that as an experimentalist per se. So there's things that you can really target that you might not have thought of before that all of a sudden come to light when you think about the facility.
Maybe just to expand on that a bit. So this risk reward landscape in research is interesting. And I'm curious, from your perspective, is there one particular place where there's the largest gap? I usually think of, ideally, academia can look at these high risk, high reward areas. And then on the extreme end, industry really tries to go for the de-risked but then scalable technologies. And is there a weakest link that we see right now somewhere in that? And this can be open to everyone.
I guess, yeah, my only perspective on that is actually what was just mentioned, the high risk, high reward. Sometimes it's hard to get funding for. And so I think I think we need to do both. But it also requires funding agencies to value high risk and I would argue that some of our high risk, high reward agencies have veered away from high risk in years. And so I think we needed to do both in academia. But generally we're well suited for high risk, high reward type problems.
Maybe I'll just add there's a interesting nuance here where you need to, the high risk, high reward might be actually the application, not necessarily the technology itself. And so thinking about opportunities for heat integration and kind of changing the paradigm of what is our target in the right appropriate market. For example, there's been so much great advancement on using hydrogen for refueling stations for heavy duty vehicles, and they're going marching ahead with high pressure and cryogenics. And there's so much momentum there that it almost makes no sense to keep focusing on that for very new, fancy, advanced hydrogen storage materials because people are just investing. They're going in, they're investing in compressors and cryogenics, and it makes no sense to replace those in the next 4 years. So we're stuck there. So now look at a different market and focus there. And so the high risk, high reward part is we now need to create these new industry partnerships, these new scenarios for the application that we just haven't thought about. And that might require a whole bunch of new experiments. So it's a cost, but it could be really directing us to that 15-year timeline.
Yeah, there's an interesting interplay here of the science and the analyses can really help to inform everyone about how best to think about these problems, but is also needing to stay close enough to the general perspective and the general understanding to get the support and to be able to make that progress. I wanted to combine a couple other questions. Maybe we have time for one or two more. And this, again, can be to everyone. Kind of going back more to the high level motivation here, there's many potential different compounds that one could convert CO2 into, and how much each one of those fully removes carbon dioxide from the entire carbon cycle can vary. Some might actually lock it away in a very thermodynamically stable compound that will not get back into the atmosphere for millennia. Some might get burned or consumed as food within the year, but without having released new fossil fuels. So maybe I'll first direct this to Dr. Zhao. I know you were looking at foods and other applications, but how we should think about the form that we are converting the CO2 into and how that plays back into the high level goal.
Sure. So I definitely can comment on that. So we actually look at the different products we can get from CO2. The key point here is what's the value of your product? So if the net value of your product is low, it's really hard to sell the new technology because everyone will compare your technology with the existing ones, right? Say, ethylene. People produce at below $1,000 a kiloton, a ton. So if you sell your technology, say, I need $2,000 to produce a ton, no one will buy it. It's really hard to sell it at least. So that's why we work on the food side is trying to find a niche point we can penetrate the market first. Because if you look at I just make it up, mushroom, for example. If you can grow specific species of the mushroom, the per unit weight of the cost could be, particularly for the electricity input, could be negligible compared to the selling price of the mushroom. So this is one of the things we need to think about is that probably mushroom doesn't take off all the CO2, of course. But then we can start to think about if we can mature our technology, make it more efficient, maybe we can target to the commodity chemicals down the road. And this is the way I think, just I learned from how Tesla becomes successful. They first are selling very expensive cars. Now they're selling Model 3, Model Y, they dominate the market. So I think on CO2 utilization, particularly using electrolysis, electrons is still expensive, we have to know. And making multi-carbon product take more electrons to do that. And that's why you need a highly efficient system and to get the price lower. So that's my take on this.
Maybe I can just add there, maybe 20 years ago, there was this just very strong debate between store versus use on CO2. And I think you noted the scale. I don't think we have time for that debate anymore. I think both are needed. And if you're in a location above a very nice formation for CO2 storage, that's what we should be doing today because we really know how to do that. It's very well characterized. We understand the subsurface very well now. And what's coming is the CO2 conversion at scales that are relevant. And as Dr. Zhao noted, it needs to start with the ones that can make it cost effective so these companies don't need to rely on policy decisions to move forward. So I think that's a really good point. And making methane, it might come in the future, but boy, is that a really hard starting place for us.
Give Dr. Hatzel if she has any thoughts on that before we wrap for the day, or if they've covered it all, it's okay too.
Yeah, no, I think that they covered it great. Yeah, it's definitely economics, and you have to do the gigaton question. Are you going to remove a gigaton of CO2 with your product and to get to giga scale? So everyone has to do that calculation.
Well, I think we've had a really interesting conversation between the wonderful talks that we heard and then the conversation we've had right now. And in just like the last 2 minutes that we have, I'm going to wrap up a little bit and say a thank you, first of all, to the three of you for being here today, and Professor Lubner for helping to organize this session. And the final question I had, which I'm going to answer for myself because we don't have time, is basically, what do you guys think we need in terms of funding? Because I think we all know the answer. Is that we need more. And I think that's one of the big challenges I see as we're talking about it. This is a huge problem at a huge scale that involves fundamental sciences, engineering, industry adoption, to really make that progress that we need right now. I think is we need a lot more funding behind large initiatives to move this forward. While we still need the small scale fundamental catalysts and other design, we need to think about this as a much bigger problem. And if I can ask the final slide to be put up for us by Sydney, hopefully. I want to thank everybody for joining us for this whole series. This was the third and final, as I said, in our series looking at working towards a zero waste world. I think these workshops are really great, bringing up some of the big challenges that we have. I want to thank everybody that joined us for the whole series, and or if you just joined us today, what I'll say is that the recordings for the previous ones are already available on the IGS website, and today's will be available in the coming days on the website as well. You can see the QR code in the lower corner, which will direct you right there. But as I said, if you registered for this event and you're here now, you'll get an email with a direct link. So I want to thank, again, the speakers that we had today for your wonderful thoughts and talks. We really appreciate you taking the time. And also I want to thank IGS, the Institute for Global Sustainability at BU, for helping to host this, along with the College of Engineering and our Energy and Sustainable Technologies Laboratory. I think altogether we brought a great community together, bringing up great challenges that we really need to address. And I hope that we will see progress on all these fronts in the coming future. And with that, I think we'll close the event. Thank you all.